Hello, so this is a quick discussion on append and remove in linked lists for C++. So a linked list has some nodes, and I'm assuming if you're watching this video, you already know that how a linked list is structured, but in case you don't, a linked list basically has a node, and it also contains a link to the next node in a list. That's why it's called a linked list. And so in order to access items in a linked list, you start from the head element or the element in the beginning, and you move down the list until you find what you're looking for, or do some operation that you're trying to do. But either way, in order to be able to access items in the list, you must always start at the beginning and traverse down the list. Obviously, there are other approaches. You can make it more efficient. There are things called doubly linked lists where links also can traverse backwards, but that's not part of the scope of this basic linked list. And today we're going to be talking about append and remove, and we're going to be using a debugger to look at how append and remove works. So we can quickly go to append first, and if I just simply set a breakpoint every time append is called, and so we have this main function here, and let's just quickly find where append is called. Okay, so over here we see that append is going to be called inside this function. Okay, and this is part of a test for the main program. It will add some items and then check whether or not it actually exists in that item. So it's testing whether or not our linked list is actually working. That's all. And so how you might expect a linked list to work is you have some nodes, and in order to add something to the end, since you only know where the beginning is, you have to start from the beginning and move over the list until you reach the end in order to access the last item in the linked list. And once you reach the last item, you can add a new item to the end of a linked list. And so if you know anything about arrays in programming, you'll also know that they're a fixed size. And there are ways to, evade size limitations. For example, the array list in Java and the vector class in C++ both allow you to essentially create an array that is bigger than the size you're actually using and slowly fill it up. And once you fill close to the maximum of this allocated array, it will copy all the elements into a new array as if you never had missing space in the first place. And it's pretty common to use this kind of tactic in programming if all you need is just a basic list. A linked list solves this problem because you always have allocated the amount of space you're using for your list. At the same time, you can always add an item to the end in case you want to add an item. So this gets around size limitations and is, the perfect way to store a list in terms of size. Instead, we're going to look at append. We're going to step into this program. So I've set a breakpoint here. So if we simply go and run this program, we'll see after a couple of seconds it stops at this breakpoint, and we'll see that there are some variables located in our memory. And so we see right now we have value. So we're inside a node. Okay. And we're looking at the value of the linked list and the value of the node. And so the value of the node is 100. This refers to the location of the current node, which is this address on the stack. We don't actually care what the address is. We kind of do, but it's some address, and we're able to access it. That's the important part. And we also are given a pointer to the next item. Here we can see that this is kind of arbitrary because what it actually is so if we simply look up at node, we'll see that the default initialization is null pointer. And so right now this is just garbage data. We don't actually care what it is or what it looks like, and it's not relevant to us, at this current moment. So we can continue running the program. Let's see. And now we're inside here. Oh, I accidentally set a breakpoint. Okay, we'll continue running the program, and now we're back. And so let me drag this over here, and we go look at the main program. So over here on the bottom left side is the call stack. So right now we have a breakpoint on append. But not only is append isn't just a function that runs by itself, it's called by append item, which we earlier looked at, and we said, oh, it's from the main function, okay, from this function called append item. Append item is called by do append and find tests. So let's see, oh, where am I? Okay, so right here, so we can see that this function is called do append and find tests. And what's going on here is we call append item with 200, some random list, or actually our linked list and some random list. I believe this is a vector. Actually, it's just a list. It doesn't matter. It's some arbitrary list that's already been defined, and we already know it works. So the implementation, which for in this case we're going to learn about linked lists, but the implementation is abstracted away from us, and so we don't actually care how it's implemented. We just know that it works. And what we're saying here is if not append item. So if we go take a look at append item again, what we see is that it calls matches. So if we simply go look at matches, we'll see that it will return false if the linked lists are not identical, and true if the linked lists are identical. So if we go back to this function, we'll see that basically we'll add 200 to both lists, and if 200 exists in both lists, then it's true, and we don't have to worry about it, and we don't return this failure, which we can see is just some 200 error code. Okay. This is called by do basic tests. So we see that there's lots of different tests, but that's the one we care about for now. And so if I move back here, we see that we added 100, which is what we saw earlier, and then we added 200. And so if we continue running the program, next we'll make it to do remove tests. Okay, so now we've talked about append. Really quickly, we can talk about how append works. So before I set any more breakpoints, we'll see that we create a new node. This node will store whatever value we're trying to look at, and then we'll create a pointer to our root node. And what we're doing here is we're looking for the end of our root node. So first we have to check whether or not there's anything even in our linked list. So in the event that there's nothing in our linked list, then we just want to create a node and return it, and we're done. But there is also, of course, the possibility that there are items in our linked list, and so we want to traverse the end into the end of the linked list before we add anything to the end of the linked list. So as long as the next object in our currently looked at node is not null, so therefore it exists, then we want to actually update our current frame of window to the next node. And it just does this until we reach the end. This is actually a good spot to add a breakpoint. So let's stop the program. And let's run it again. So we're going to see the same thing. We're going to see 100 get added and then 200 get added. And now we're at the breakpoint already. And oh, it looks like we're at 300 this time. Let's go take a look. Oh, we're already at do remove tests. So let's restart this program. Somehow we skipped these tests. I don't know why. Stop. We need to start over. Okay. Oh. Something's happening. Okay. Okay, let me drink some water. Cool. For some reason, we're not starting at the beginning anymore. This is strange. Maybe this is what I get for not using a new debugger than what I used last time. Let's see. Well, it doesn't matter. Regardless, you get the idea. This is how append works. And so now we actually won't care about how remove works. So before I get to the end, let's kill this program. And make sure there's nothing in here. Okay, there's nothing in here. Cool. Something running here. This can die too. And this can die. Okay. Interesting. Okay. So next we're going to talk about remove. And so remove is somewhere here, so we can actually bring up the outline. And we can see that remove is actually declared here. So we can take a look at the declaration real quick. Remove takes a value. And what we expect to happen is we expect that if there exists some object that we can remove, we'll remove it, and then we'll return the node. And if it doesn't exist, then we'll return nothing. That's what we expect. Okay, let's delete these comments. They're just print statements. So what we're looking at here is we first set our frame to the root, and then what we want to do is you want to look for the node. So if we make it to the end, and oh, actually this isn't the beginning. So first of all, we have to make sure that the root is not the value. So if our root contains the value, we just want to return that right away, and then we're done. However, what we want to care about is we have to also keep track of the previous node, right? So if we're at the root, there is no previous node. And which is why we have to check that first. However, if there is a previous node, then we look for basically the current node, whether or not it equals the value. And if it does, then we drop the current node and we set the previous link to the next link. So what this means is basically if there's like some sequence, 1 that links to 2, that links to 3, and I want to drop the 2 in the middle, I have to link 1 to 3. So basically I'm deleting the 2 and replacing it with a link from 1 to 3. And if I find this node and I delete it and I update the link, then I want to return the node. However, if this doesn't happen, then I'll make it to the end and I'll have to return nothing. So that's how remove works. So we can maybe set a breakpoint, let's say here in the while statement as well as in the root node, and then we'll run this program. Okay, so right now we're looking at node, which is something random. Some address, but it's 100. Okay, so let's look at our call stack and see what we expected. We're at remove right now. We move up 1 on the call stack. We see that it was called by remove item. It looks like identical to the append item test, where we have some list and we have some remove item, and we just want to make sure that the lists are the same. So let's see what value we're trying to remove. So we move up the stack. We see now that we're looking at remove tests, we have some list here that has 100, 300, 400, 200. And so we're at the first item. We want to remove 100. And so that's the item we're trying to remove, and it exists in the front, so it should return here, and we're done. Next, the program runs, and now we have 200. And 200 doesn't exist at the front, and we want to remove 200, and so it gets moved in the while loop, and so on and so forth. Okay. And so on and so forth, and until it's done, and we remove all the items. And that's how the remove works. So this is a quick overview over how append and remove work in a linked list for C++. Thank you for watching, and yeah.